This is my Lab 5 for gravity and drag. This is my video, which shows a person holding a water bottle and a piece of paper and then dropping them. In order to complete this assignment, I made two separate tracker videos, one for the bottle, one for the paper. In the bottle video, as seen here, I used the bottle as the calibration stick, where the calibration stick was 0.00765 meters, which was the width of the bottle. For the bottle, the origin I placed at the bottle, with the point mass at the bottom of the bottle, and follows it as it falls. The axis is on a negative 1 degree slant to best follow the path of the falling bottle. I chose frames 68 to 85 of the video in order to encompass the full fall of the bottle. The total time of this video was 0.6 seconds, and the total distance that the object fell was 1.7 meters. As you can see here, when the video runs, the point mass follows it to the bottom where it impacts. The other tracker video showed the paper falling. The origin I set at the paper, and the point mass was at the crease in the paper. On this one, the axis was on a 0 degree slant, as the paper, when it fell directly downward. I chose frames 68 to 103 to encompass the paper drop, as due to the drag, it fell slower. So the total time for this video was 1.14 seconds, and it fell a similar distance to the bottle, which was just over 1.7 meters. As you can see here when it runs, the paper falls much slower than the bottle does. In order to finish this assignment, I had to create 4 different models to simulate both objects with and without drag. The first model showed the bottle dropping without drag. I used 0.181437 as the mass of the object, with a time of less than 0.6 seconds. The F-grav, or the force of gravity, was negative g, so 9.81 times the mass, which I then used to calculate the ball velocity. When you run the model, you can see that the arrow shows the constant force of gravity on the object. The same thing was then done for the paper dropping. The only thing that was changed was that the mass was different at 0.006245 grams, and the time was double the length at 1.2 seconds. If I run this, you can see, as in the last one, there's a constant red arrow showing the force of gravity and the curve of the velocity of the object. I then had to make models for both the bottle and the paper dropping with drag in effect. For this, I used the same mass as previously, 0.18143, and the same time of less than 0.6 seconds. In order to find F drag, or the force of drag, on the object, I found the magnitude of velocity times a negative number. The force of the drag and the force of gravity were then combined to find the total net force on the object. In the simulation, the upwards blue arrow shows the force of drag on the object as it moves downward. I then did the same thing for the paper dropping, using the paper's mass of 0.006245, and using the same physics concepts, where F drag was the magnitude of velocity, and then the combined total net force on the object was the force of drag combined with the force of gravity. Here, you can see again the upwards blue arrow, which is much larger on the piece of paper. Then I compared the models. Here, The first two graphs, as shown here, show the model, both the model for paper and the bottle, without drag on the objects. You can see that without drag, the object is moving much further, at -7 meters for the paper, and almost -2 meters for the bottle. The next two graphs showed the model with the drag, and for both the bottle and the paper drop. The difference is clear, as the introduction of drag into the system both lessens the acceleration, as the curve is not as drastic, and lessens the total distance that the object covers, as the paper only covers 5 meters, and the bottle only covers 1.5 meters. So, what does it mean? Which model predicts a terminal velocity? The answer to this is the model which includes a drag force. This is because terminal velocity is found by the point where the sum of the drag force is equal to that of the force of gravity. Thus, there is no drag, and the terminal velocity cannot be found. So, what if we examine the object's velocity in the case where the object is initially thrown downwards? To do this, we need to add an initial velocity in the negative direction. Here is the model of the paper drop with a velocity of -10 in the y direction as an initial velocity. The difference from the previous examples are clear. You can see with the initial velocity, there is an increased drag, and thus the terminal velocity is reached much quicker, as can be seen by the nearly flat line in the model. This can then be seen in the graph, where the flat line is again shown as drag is almost equal to the force of gravity, thus allowing the object to reach the terminal velocity. This graph can then be compared with the previous graphs, where you can see it's much more curved, showing how in the previous model, without the initial acceleration, it did not reach its terminal velocity. Thank you for watching. That is my lab.